All right, our next section here is on how to calculate equilibrium concentrations. We can use stoichiometry and the initial concentrations and one equilibrium concentration to calculate the other concentrations for an equilibrium situation. I find this is easiest just to work through a question and go from there. Okay, so our question, find the value of Kc for the reaction 2 methane goes to acetylene, C2H2, plus 3 hydrogen at 1700 degrees Celsius if the initial methane concentration is 0.115 molar and the equilibrium acetylene concentration is 0.035 molar. The way we solve these problems is by using something called an ICE table. So an ICE table in the top here has all of our reactants and products. You might want to draw the equilibrium arrow and put the coefficients so that you remember what they are. If I'm writing this not in a table form, I will often just write the equation at the top there. And then on the side here, we have the ICE part of the ICE table. I stands for initial, C stands for change, and E stands for equilibrium. Again, when I'm writing it, I don't write out the whole words, I just write ICE, but that's what they stand for. Then we can write in our initial values. From our question, we're given the initial methane is 0.115 molar. And if you're only given a reactant, you can assume that the products are starting at 0. And then we're given our equilibrium C2H2 acetylene as 0.035 molar. Now here is where we need to use our table. So we know that we have gained 0.035 acetylene. In order to gain that, we can use our stoichiometry, and we know that we have lost in our reactants 2, our coefficient there, times our change value there. So 2 times 0.035. And then our hydrogen, we have gained 0.035, but our coefficient up there is 3, so we've gained 3 times 0.035. And then to find our equilibrium, you always just add together your initial and the change. And remember, you're always, well, not always. You want to keep track of if you're losing or gaining, but whatever you lose in reactants, you gain in products. So if I do this math, I'm going to take my 0.115 that I started with and subtract off 2 times my 0.035, and I get a equilibrium concentration for my methane of 0.045 molar. And then my hydrogen, I started with none, and I gained 3 times 0.035, which is 0.105 molar. Now, the question is asking, find the value of Kc. Now, we have our equilibrium concentrations, so to find our Kc, all we have to do is practice writing out our Kc value using our balanced chemical reaction. So it's going to be our concentration of our acetylene times our hydrogen to the 3rd power divided by our methane squared. And then I can plug in my values, 0.035, 0.105 to the 3rd power, and 0.045 squared. Then I can find a Kc value. So my Kc is equal to 0.020. I would make sure when you're typing this into your calculator that you have enough parentheses around things, because otherwise it's very easy to come up with the wrong answer on these. So here's all that math worked out again. Here's our next question. I would recommend pausing the video and working this through and then checking back to make sure you did it correctly. Consider the reaction iron 3 plus thiocyanate goes to iron thiocyanate. A solution is made containing an initial iron 3 concentration of 1 times 10 to the minus third molar and an initial thiocyanate concentration of 8 times 10 to the negative fourth molar. At equilibrium, the product concentration is 1.7 times 10 to the minus fourth molar. Calculate the value of the equilibrium constant. So this is very similar to the last question. We have our iron 3 plus our thiocyanate in equilibrium with this complex ion. We are doing an ICE table. We are given our initial concentrations. We can write those in. And our initial product is 0. We gain 1.7 times 10 to the negative fourth, because that's our equilibrium concentration of our product, which means we lose that in our reactants. So now I just have to add my initial and change together for my reactants. So for my iron 3, I get 8.3 times 10 to the minus fourth. For my thiocyanate, I get 6.3 times 10 to the minus fourth. Then I know that my Kc is going to be my complex ion here divided by my iron 3 times my thiocyanate. And so my Kc is going to be 1.7 times 10 to the minus fourth divided by 8.3 times 10 to the minus fourth times 6.3 times 10 to the minus fourth. If I do that math, I get an answer of 325, which is the correct answer. I don't have it on the next slide, but all right, another one to work through. Consider the reaction below. Complete the table, assuming all concentrations are equilibrium concentrations in molarity. So we're given concentrations, and we want to calculate these various things from what we know. So the first line should be pretty straightforward. We know, I'm just going to write it here, that our Kc is going to be our ammonia squared over our nitrogen times our hydrogen cubed. So that's pretty easy to figure out for our first line there. You can just plug in the numbers and get a value of 1450. For our second one, it's going to be a little bit trickier. So we know that our Kc is 9.6 is going to equal our ammonia is 0.128. That gets squared divided by our 0.110 times our H2 cubed. So now we have to rearrange and solve for our H2. So our H2 cubed is going to be our 0.128 squared over 0.110 times 9.6. Then we can solve for our H2, solve for the cube of it, and then take the cubic root, get an answer of 0.249. Then for our last one, it's going to be very similar. In this case, our 0.0584 is our ammonia squared over 0.120 times 0.140 cubed. So we can take these, multiply over here, and then take the square root, and we get an answer of 0.00439. And you can see that this makes sense. So as we increase in temperature, our Kc value is going down. Kc is temperature dependent. And as our Kc goes down, you can see our amount of product also goes down. When we have a very low Kc value, we are not getting much product at all. So there's the answer. All right, this next question is getting into kind of our next topic, which is what happens when we shift an equilibrium and we know our K value, but we don't know our equilibrium concentrations. So in this case, our question is saying what is happening if we mix together 1.2 atmospheres of NO2 and 2.4 atmospheres of N2O4. We have a given Kp value. We need to decide first which way is our equilibrium going to shift. That's what this Q is about. Remember, we learned about the reaction quotient, Q, and that would be our 2.4 divided by 1.2 squared, which is 1.67, which is larger than our K value, which means we're going to shift towards the reactants in order to bring that K value back down. When we shift towards the reactants, we're going to lose some unknown amount of our product. So we're going to say it's minus X. And we're going to gain a related amount of our reactant. But because we have a 2 here, we're going to gain twice as much as we lose of our product. So we're going to gain 2x in our reactant side. So at equilibrium, remember for our equilibrium, this is just a nice table. At equilibrium, we're just adding together our initial and our change. So at equilibrium, our reactants are represented by 1.2 plus 2x. Our products are represented by 2.4 minus x. Then we can just plug those in to our equilibrium expression. Now the question is a multiple choice. What is the expression? So we know it's 0.98. Our product is 2.4 minus x, and there's no coefficient, so that narrows it down to A and B, divided by 1.2 plus 2x. But because we have that 2 coefficient, it's squared. So our answer there is B. And let me write it the way our 0.98 is going to be 2.4 minus x over 1.2 plus 2x, and that one gets squared. Now you can see that this gets fairly complicated quickly because of that coefficient. We're going to end up with a quadratic equation, and in this class, I don't expect you to solve the quadratic equation. I just need you to be able to get to this point. Unless there's an exception that we will talk about soon that will get us something that makes it so that we can solve this equation. It doesn't apply to this question though. Okay, so more work here. Another table to fill in for practice. Solve for the equilibrium partial pressure. So if you are feeling a little shaky on ice tables and understanding how to do this, I would work through and try to solve these at least to the point where you have an x value. In fact, just to the point where you have an x value, because to solve it, you'll need to use either the quadratic equation, or you could plug it into something, into a program on the computer to solve. So let's work through this one here a second. We know our ice table here, our initials are of N2O4 is 2.20, our initial of NO2 is 1.10. And 2.20 over 1.10 squared gets me a Kc or a Kp value of 1.8. My Kp here is 56, so 1.8 is a lot smaller than 56. So we're going to shift to the product side to bring up our value. So plus x, and then we will be losing from our reactant, so minus 2x, and the 2 is there because of the 2 here. So at equilibrium, we have 1.1 minus 2x and 2.2 plus x. And then again, you would have to solve it using either the quadratic, or you could go online and solve it. You won't have to do that on a test. Just get to this point where then you know that 56 is equal to 2.2 plus x over 1.10 minus x squared. Okay, here's another one. We're not going to use the quadratic. I didn't take that out. I used to do one practice one with it, but we are not going to do that. But let's work it through to the point where you would need the quadratic. So we have I2 in equilibrium with 2I, the value of Kc, 3.76 times 10 to the minus fifth. If 1 mole is placed in a 2-liter flask and heated, what will the equilibrium concentrations be? So 1 mole in a 2-liter flask means we're at 0.5 molar. Our equation, let me change color so it's easier to pick up, is I2 in equilibrium with 2I. Oh, there's no minus there. 2I. Our initial, we have 0.5 and 0. Then we have a change, and equilibrium, we're going to be going this way, so plus 2x minus x. Then for my Kc is 3.76 times 10 to the minus 5. And that's going to be my product, 2x squared, over my reactant, 0.5 minus x. And you can see there that now I'm going to have an x squared, so I would need to use my quadratic to solve it all the way. But for this class, all you need to do is get to here. Okay, here's another problem. This one, let's just work it through. I don't think you need the quadratic, but I'm not positive. Okay, so we are going to write down our equation. SO2Cl2 is in equilibrium with SO2 plus Cl2. We have our initial, our change, and our equilibrium. Reaction mixture is made containing an initial of 0.020 molar. And if you're only given reactants, you can assume your products are 0. At equilibrium, the Cl2 is 1.2 times 10 to the minus 2. Calculate the value of K. So we know our change has been 1.2 times 10 to the minus 2. All of our coefficients are 1. So our our equilibrium concentrations of our products are the same. Then we're going to subtract over here and get our equilibrium concentration of 0.008 molar. Then my Kc is going to be 1.2 times 10 to the minus 2 divided by 8 times 10 to the minus 3. And I don't need my quadratic equation for this, so I can just plug everything in to get an answer of 1.8 times 10 to the minus 2 as my answer. All right, I mentioned we don't usually use the quadratic because there are simplifications and approximations that can help us. So when our equilibrium constant is very small, the position of equilibrium will favor the reactants. And when we have large initial concentrations of reactants and a small equilibrium constant, the reactant concentration is not going to change significantly when we reach equilibrium. So we can approximate that our equilibrium concentration is about equal to our initial. If we take our initial and subtract off that X value, it's going to be very small. We're going to treat them as the same number, assuming our reaction is progressing forward. Now there is a check you need to do, which is by comparing the approximate value of X to the initial. So if you take your approximate X, when you get to that step, divide it by the initial concentration and multiply by 100%. If it is less than 5%, you may use the X as small approximation. Now again, I find this much easier to understand if I just talk through an example. So let's work on an example. For the reaction, 2 H2S is in equilibrium with 2 hydrogen and 2 sulfur at 800 degrees Celsius. We have a very small Kc value, 1.67 times 10 to the minus 7. If a half-liter flask initially containing 1.25 times 10 to the negative 4th moles is heated to 800 degrees, find the equilibrium concentrations. So we're going to start by writing out our equation. So 2 H2S is in equilibrium with 2H2 plus S2. We have initial, our change, and our equilibrium. So our initial, we have a half a liter flask, 1.25 times 10 to the minus 4th moles, which means my molarity is the 1.25 times 10 to the minus 4th divided by 0.5, which is 2.5 times 10 to the minus 4th, and we don't have any product to start with. I'm going to lose products, so minus my coefficient 2x. I'm going to gain, I'm going to lose reactant. I'm going to gain products, so plus 2x plus x. So at equilibrium, my reactant will be 2.5 times 10 to the minus 4th minus 2x. My products will be 2x and x. I know my Kc value, 1.67 times 10 to the minus 7th, is equal to 2x squared times x divided by 2.5 times 10 to the minus 4th minus 2x squared. And now we're going to use our x's small approximation. So we're going to get rid of this minus 2x in both of those places. So that means that with our x's small, we're going to have 4x cubed on the top, 2.5 times 10 to the minus 4th squared on the bottom. That I can solve with just a single 4x cubed. So I can find that now my x is equal to 1.38 times 10 to the minus 5, which means that I need to check my x's small approximation, and in that case I'm going to take my x, 1.38 times 10 to the minus 5 divide by my initial 2.5 times 10 to the minus 4. And if I do that, it times 100%. I get a value of 5.52%, which means that technically my approximation is not valid. But if you go through and solve it the other way, you'll get a very close value. You can also, if you plug this value of x back in over here where it disappeared and then solve for x again, you'll get an even closer approximation. So the point of this problem was mostly to show you that you need to check your x is small approximation, and if it's not valid, then you need to find another way to solve that equation. So if this were the answer, that's what you would get for your equilibriums. As it is, this is not the best answer possible. Okay, here's another practice, and it tells us we can use the simplifying assumption to solve for x. We've looked at this one before, so our reaction of I2 goes to 2I, our initial, our change, our equilibrium. So our initial 1 mole in a 2 liter flask is 0.5 molar. We're going to lose some of that, gain that. So our Kc we are given is 3.76 times 10 to the minus 5 is equal to 2x squared divided by 0.5 minus x. But again, we're going to use our x is small, which means we can ignore that x there and solve for our x. So 3.76 times 10 to the minus 5 times 0.5 is equal to 4x squared. So I can find my x is 2.17, there's a decimal in there, times 10 to the minus 3. If I take 2.17 times 10 to the minus 3 divided by 0.5 times 100%, I get 0.43%, which is much less than 5, so this is a good substitution. And it's asking for the equilibrium concentrations. So my equilibrium concentration of I2 is going to be 0.5, which should be 0.500 minus 2.17 times 10 to the minus 3. I get an answer of 0.4979, or with sig figs it's going to be 0.498. And then my concentration of I is going to be 2 times 2.17 times 10 to the minus 3, which is 4.34 times 10 to the minus 3. So don't forget to go back and plug in your values to get your equilibrium concentrations. Don't just stop at solving for x. Okay, we have a couple more. One more question here. The answer is already here. You can work through that one. If you have questions on it, please feel free to email me.